the electromagnetic spectrum. Now you're going to want to draw this entire diagram, all parts. What you're looking at are the wavelengths of the electromagnetic spectrum. As we go from radio waves all the way through to gamma rays, you can see that the wavelengths get shorter and shorter and shorter as the energy and frequency get higher and higher. Now, I'll show you a simulation in a few minutes that'll better have you understand exactly what's going on there. But again, you want to draw all of this, including, hopefully you have some colored pencils where we're going to blow up the visible portion of the electromagnetic spectrum, all the colors. Roy G. Biv, you may not know, but that's an acronym that we use to remember the order of the colors. So it stands for red, orange, yellow, green, blue, indigo, violet. So as you can see, as you go from radio waves, microwaves, infrared, then we would hit red light and go through all the colors of the rainbow. And when we get to violet afterwards, we get to ultraviolet, X-rays, gamma rays. Now you don't need to know these numbers up here, and this nm is nanometer, which is a billionth of a meter, but you should have a general idea of the range. So radio waves of the order of 100 meters, that's from crest to crest, and it goes all the way down to 10 to the negative 10 gamma rays, and that's in the order of the size of the nucleus of an atom, incredibly small. Okay, I'm going to show you a short video on the electromagnetic spectrum. It's about 3 minutes long.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 123. It's on electromagnetic radiation. Newton had shown that if you shine white light into a prism, it breaks it apart into its different colors. And another scientist wanted to know, is there any relationship between different colors of light and the temperature? So William Herschel took a thermometer and put it in the purple light, and in the blue light, and the green, and in the yellow, and in the red, and he wanted to figure out where were the different temperatures depending upon color. But he wanted to have a control in this experiment, so he put another thermometer right off on this side just to judge the room temperature. And what he found, surprisingly, is that that was the hottest temperature of all. So he really discovered was infrared rays. And so those are rays that we can't see but generate a lot of heat. And so electromagnetic radiation, we only see a small sliver of that called visible light. But there's a whole bunch of other electromagnetic radiation out there in the universe. And we can put it on a spectrum and measure it from the really low, small wavelength to really long wavelengths up to kilometers in wavelength. And then on the other direction, we're going to have increasing frequency. So as we increase frequency, we're going to decrease that wavelength. As we increase frequency in electromagnetic radiation, we're also increasing the amount of energy that those waves have. And so if we start with really high energy, we would have gamma rays, then X-rays, then infrared, and then visible light. So you can see that we're just seeing a small sliver of electromagnetic radiation. We then move into ultraviolet, finally into microwaves and radio waves. And so inside this room right now, I have visible light, but there are also radio waves here. That's how you could pick up a radio signal or a TV signal. But I also probably have microwaves in here as well. Hopefully I don't have too many gamma rays in here right now. But if we put them along a spectrum, they're going to decrease in wavelength as we move towards those gamma rays. To give you a sense of scale, radio waves are going to have wavelengths around the size of a building, but gamma rays down around the size of a nuclei. And there's this inverse relationship. So as we increase wavelength, we're going to decrease the amount of frequency. And so as we increase frequency, we have higher amounts of energy. So which one would you rather be exposed to? These ones with long wavelength, really, really low frequency, low energy. The ones on the right side are going to be able to damage cells, ionize cells, cause damage to the cells itself. And so did you learn to just make qualitative comparisons based on wavelength and frequency of electromagnetic radiation? I hope so, and I hope that was helpful.
Okay, now here's another diagram. You don't necessarily need to copy this one down, but it's a nice visual. Increasing frequency as we go to the right here, increasing wavelength as we go to the left. They're opposites. As one increases, the other decreases. Now, where does electromagnetic radiation come from? All electromagnetic radiation comes from the movement of electrons. Really anything that has a charge, but mostly it'll be electrons that are responsible for electromagnetic radiation. Now let's look at this in a little bit more detail. If we were to look at a single electron, what we have emanating in all directions is that negative charge moving or going out in all directions. We refer to that, or we can represent it by what's called electric field lines. So they're not actual lines, they're just a region of space where that negative charge emanates. So let's look at one of those field lines. Now let's rewrite this down below, so let's just have that one line that we're looking at. Now imagine if I was to take this electron and move it up and then move it down. Well, as you might guess, the electric field line would move with it, just like if this was a rope and you were to take that rope and move it up and down, well, then you would start having a wave forming. And it'll look something like this. So an electromagnetic radiation is simply electrons moving, oscillating up and down from one place to another place, and the electric field line moving along with it. But just like if this was a rope, the rope wouldn't actually be moving, just the energy would be moving. Like if you were holding the rope on one side and another person was holding on the other side, and one of you starts moving it up and down, well, the rope doesn't move, just the energy transfers through the rope. And so that is what we mean by electromagnetic radiation. The electric field lines transmit the electromagnetic radiation. So something like radio waves, well, the electrons are not moving very fast, whereas gamma rays are moving incredibly fast, giving off a lot of energy. Okay, now these are the parts of a wave, and you need to understand all the components of a wave. So you need to draw this entire diagram, label all these parts. Now, the highest point of a wave is referred to as the crest, and the lowest is referred to as the trough. The distance from any one point of the wave to the exact same point in the next wave is called a wavelength. Typically, it's measured from crest to crest. Wavelength is given the symbol lambda. It's a Greek letter, looks like an upside down italic Y, represents wavelength. So here it's a wavelength. The frequency of a wave is how often a wave passes a given point over a given amount of time. There is a unit that we use for frequency called the hertz, which is 1 wave per second. So imagine that these waves are traveling across here, and if I was to count the waves as they pass, let's say this point right here, let's say if I had 1 wave pass in a second, well then we would say that the frequency is 1 hertz. If I had 100 waves pass in a second, then it would be 100 hertz. Frequency is given the symbol nu. It's a Greek letter, it looks like an italic V. In recent years, it seems as though I'm more and more seeing just capital F representing frequency, sometimes lowercase, but I'm a traditionalist, and I learned it as nu. Still being used, but I'm just saying that you may see it as F. And then one last thing, the amplitude is the height of the wave. Now, you know that we have FM radio and AM radio. FM stands for frequency modulation. So they changed the frequency for FM radio. AM is amplitude modulation, where they modulate the amplitude of a wave. Different ways of communicating information using a wave. Now, the speed of any wave is the wavelength times the frequency. For light, the speed of light is 300,000 kilometers per second. It's ever so slightly less than that, but rounding 300,000 kilometers per second, which is about 186,000 miles per second. That's an incredibly fast speed. It's over 7 times around the Earth in a second. It's like 1 1,000, 2 1,000. You just went around the Earth 7 times. So very, very, very fast. And in fact, it is the speed limit of the universe. Nothing can go faster than the speed of light. It was one of Einstein's big insights with his special theory of relativity. If you are interested in that, if that seems intriguing to you, look up the special theory of relativity. Okay, now if we multiply the wavelength and the frequency of an electromagnetic wave, we would always get the speed of light, c. Now, we're not going to be doing calculations with this, but you will be responsible to know the relationship. Know that c is the speed of light and what the speed is, and wavelength and frequency. Now, what this means is anytime you have two numbers that you multiply together to get a constant, that means that those numbers are inversely proportional. It means as if I increase one, I would have to decrease the other in order for the product of the two to always give me the same number. In this case, the 300,000 kilometers per second. So wavelength and frequency are inversely proportional, which means as one gets larger, the other gets smaller. Okay, let me show you a nice little simulation of the comparison between wavelength, frequency, and energy. This is a PhET simulation. Okay, so we're kind of moving a chain up and down here, and I can change the frequency, but it's kind of better to think of it as energy. So let me kind of slow it down here. So you can imagine that, so this is very low energy. You can see that the wavelengths are really long, not very many pass a given point over a certain amount of time. But if I increase the frequency, which is again kind of easier to think about increasing the energy, like turning up the speed of the motor, say, more energy. So you can see that the number of waves that pass a given point over a certain amount of time increases. So we now have greater frequency. Oops, all right. So if I was to count the number of waves that pass a given point, now I have quite a few passing. So the wavelength has gotten shorter, but the frequency has gotten higher. So let me again kind of go to the two extremes here. So low energy, low frequency, long wavelength. Conversely, here I would have high energy, high frequency, which meaning many waves pass a given point over a given amount of time, and very short wavelengths. A continuous spectrum contains all the wavelengths of visible light. So Roy G. Biv. It's continuous spectrum. So it's all the colors of the rainbow. So here we're just looking at visible light. Now compare that to what's called an emission or line spectrum, which contains only certain wavelengths of visible light. So in this case, we just have 4 bands of color. Kind of think of it like a barcode of color. Well, what exactly is going on here? Let me show you a little animation. Now, it turns out that atoms are responsible for this.
Late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors.
So this is hydrogen gas, and if electricity is passed through it, it gives off this color, this lavender color, but it's really made up of different colors. And if you pass it through a prism or what's called a spectroscope, you could break the colors into, the color into its components. And so that's what we mean by a bright line or emission spectrum. Every element emits its own unique emission spectrum that can be used to identify it, similar to a barcode. So here's 4 elements: sodium, hydrogen, calcium, mercury. If you were to take any one of these elements and vaporize it so that it's a gas and then pass electricity through it, it would give off a certain color. But if you pass that color through a spectroscope or through a prism, it would break it apart into its components. And each one of these elements has its own unique pattern of light, which is an amazing thing. It means that light itself, hidden within light, is a great deal of information. When we look at the stars, how do we know what the stars are made up of? They're so incredibly far away, this tiny pinpoint of light. Well, we know that by passing the light through a spectroscope and breaking the colors apart, and we can identify the elements that the stars contain. It's an amazing thing. Although emission spectra was easily observed, no one could explain why atoms did this. And this we're talking like the 19th century. Also recall the problem with Rutherford's model of the atom. Electrons should lose energy and crash into the nucleus. So we have two problems that don't necessarily seem to be related to one another. What causes the emission spectrum? Nobody knew. And why don't electrons crash into the nucleus? Nobody knew. Well, as it turns out, the two are directly related. And it took an amazing, amazing scientist who came to work with Rutherford to offer a pretty impressive explanation, not just for the emission spectrum, but for why electrons don't crash into the nucleus, which are, again, related. So fortunately, in 1912, a young man from Denmark came to work in Rutherford's lab who had some amazing new ideas. His name was Niels Bohr, and he will be the topic of our next set of notes. But for now, this will be continued, and we are at the end of today's notes.